Hello everyone, I'm Mr. Neththikumara and I'm going to present here about my work on Linac optics optimization with multi-objective optimization, which is a part of the beamline redesigned for multi-pass multi-GeV energy recovery experiment here at CBAF, which is proposed at CBAF Accelerator. This is the layout of CBAF Accelerator. In general operations, electron beam accelerates up to 12 GeV with 5 accelerating passes throughout the machine, and for here at CBAF we will have additional 5 decelerating passes, and in order to decelerate the electron beam we have to install a path length chicane at the arc A, and also to dump the decelerated low energy beam we will have to install a low energy beam dump at the end of the south Linac. The Linac energy gain is scaled up to 750 MeV in order to compensate the synchrotron radiation losses. For this study, we created a 10-pass North Linac beamline as shown here. Accelerating passes, we use the North Linac elements as they are, and for decelerating passes, we arrange the elements in a reversed order, and the accelerating and decelerating passes are connected with the zero length matrix M to match with the arc optics as we prefer. There are 27 quadrupole magnets in North Linac lattice, and in manual optimization we tune those quadrupole focusings and initial twist values by checking the twist output of the beamline. This optics plot corresponds to a manually optimized solution, and as we expect to suppress the beam breakup instabilities, the low energy pass, first pass twist functions are controlled very tightly. Beta values are less than 50 meters here, but the higher pass Linac end values have significant difference, and our goal is to minimize this difference and have mirror symmetric variations. With multi-objective evolutionary algorithm optimization, we will get multiple solutions instead of few, and we use 3 objectives in this optimization problem. These are the 3 objective functions we used in our study. The first objective function is responsible for keeping horizontal and vertical beta variations very closely. For this, we calculated the moving averages of beta x and beta y and calculated the mean squared error and tried to minimize it. The second objective function is responsible for minimizing the peak beta values. We expect to have peak beta values at the end of each pass, but these peak values should not be very large. We consider a margin of nearly 300 meters, and the peak values should be within that limit. The third objective function is responsible for minimizing the difference between the adjacent peak beta values, which help to preserve the mirror symmetry variation we prefer. And we will get a set of solutions with our evolutionary algorithm search, and we called it as a optimal front. And along with these 3 objectives, I used 2 constraints to preserve the quality of the optics of the solutions that we obtained. With 26 quadrupole fields and for initial conditions, our problem became 30-dimensional, which required a large population size and eventually a large computational time. But our main challenge is to reduce this computational time. Therefore, we performed a field variation analysis of the Pareto front solutions that we obtained for 30D problem with 500 population size for 200 generations. And this box plot represents the field variation for each 26 quadrupole. And as you can see, many of the quadrupoles do not vary very largely, so we can reduce the variable space for each quadrupole. Then we can reduce the search space, and it will eventually reduce the computational time. Here I have put 3 solutions from 3 different search problems with generations 200, 225 and 250, and here you can see the mirror symmetric variation gets improved with 225 generations, and also the peak beta values were reduced with 225 with 250 generations. Analyzing the results that we obtained from each search, we can arrive at these conclusions. That is, we need an adequate population size and generation numbers due to the large search space we have, and this search space can be reduced by performing a relevant field analysis, and by limiting the search space we can reduce the required population size and the computational time. The most important thing is from the results we obtained from this evolutionary algorithm multi-objective optimization search are in good agreement with the multipass optics requirement. And as for the future work, you can use this 10-pass North Linac optics settings to create a 10-pass South Linac beamline, and by doing that we can build up a 10-pass beamline for here at CBEF lattice, and then we can perform a study of beam ellipse evolution with this redesigned beamline. Here I have listed some of my references, and please leave any questions you have below. Thank you.